So, we are back to talk to you today about potential energy diagrams. So, the top of the sheet that you have, we're not going to really go over it. We're going to go into it in more detail later. But we do have a special guest with us today, Miss Vampus. Would you like to say hello?
Hello, everybody. I feel like it's been a long time since we have, conversed together. Um, anyway, yes, today we will be talking about potential energy diagrams. And if, like Miss Scanlon said above, you should have just looked at the two images and just compared, the differences and similarities between the two. And now we're just going to go ahead and highlight some of the things that this lovely conversation between Jon, Daenerys, Sansa, Arya, and Bran are having, okay, and about their homework assignment. So let's go ahead and do that.
Okay, so there's so much reading. We're not going to go through all of it. You can read that on your own, so pause the video and read it, or you've read it before. But again, we just want to highlight the key terms. So one of the first things is that we're talking about these kind of roller coaster looking things, and these are potential energy diagrams. So it's used to kind of show how the potential energy changes throughout the reaction.
Right, so one of the things that we want to just review with you guys, we're going to review it when we are annotating the diagrams, but just remember what the reactants are, okay? And on the diagram, we're going to show you later on as well. And also keep in mind where the products are as well. Those are two terms that we really want you to highlight and remember. Okay, we've spoken about those terms. And just keep in mind that we're going to be using them again.
Okay, so again, this will make more sense when we apply it to the actual picture, but we're just kind of throwing out these new words at you now. So the next thing we want to talk about, or at least highlight, is the reaction coordinates. Just like Ms. Vampus had said, essentially we're tracking the energy of the reaction. So how energy changes from what the reactants are to what the final products are. And again, the graph will track this kind of energy change.
Ms. Scanlon, just to help us out here, what bullet are we targeting right now?
Right now, we just highlighted part of what Jon had said with the reaction coordinates, and then Bran saying it shows the progression of the reactants.
Okay, got it.
Okay.
Okay, let's move downward.
Moving forward, again, we have talked about before if something was exothermic or endothermic, and when, as I'm highlighting now, Sansa can tell you the difference between exo and endothermic based on these graphs. So that's something to keep in mind when we're looking at these actual pictures later on. Just a quick note as I'm highlighting here. Jon makes a quick joke about hydrogen bonds being not actual bonds. So yes, that's not part of this technical unit, but it's important to remember these are intermolecular forces, which did play a part in last unit. Okay. Moving forward, again, it definitely helps if you kind of pause this and read through the video because we might not catch on everything that the reading has to offer.
I do want to just point out that peak, right, which is known as the activated complex. That's also an important term that you should keep in mind. And we will be labeling that, and that is something to know. And especially when we are talking about catalysts, that will be important as well, the activated complex. Okay, so moving forward, what are some other things that we should highlight?
So looking forward, one of the other things is, one of the things we talk about is sufficient energy, and we'll get to that later on. But an important thing we'll mention today is a catalyst. So if you think back to your living environment class, you've mentioned it, and you probably, even if you don't remember the definition, you remember talking about it. And essentially something that speeds up the reaction. And we'll show you how it actually speeds up the reaction and the chemistry behind that speed, essentially.
Essentially. Yes. Wait, when do we talk about catalysts for living?
You can talk about enzymes.
Oh, yeah. Enzymes. Yes. Yes, we just taught this actually. That's right. So when catalysts are involved, guys, like this will drastically change the curve of the graph. So we're gonna highlight that when we annotate it. All right. So just remember, catalysts speeds up things. All right. So does that wrap up like the highlights of the reading?
I think so. Definitely go back, actually read it to make sure we didn't miss anything. But let's now jump down to potential energy diagram number 1. So we're gonna go through this together and have you guys kind of apply this to the graph after. So looking at it, one of the things we pointed out in the reading was something called the reaction coordinate. So if you think to how a reaction actually happens, you're starting with your reactants. Again, in order for a reaction to happen, you need your reactants. And then you're producing your products. So the very start, I can't spell products. The very start of the reaction represents your reactants. Stuff happens, out pops your products, which you produced. So, looking at this picture, again, this is the potential energy diagram, and that's what the y-axis is showing. It's showing how the energy changes throughout the reaction. So if we're going to look at point A, so let's label the diagram first, and then we'll jump through the questions. So if we know the reactants start at the beginning of the picture, point A represents the potential energy, so I'm going to abbreviate it PE, of...
PE is going to stand for potential energy, okay? And point A, we're just going to label that. Miss Ganlon's going to write it, annotate the diagram as we're speaking, is going to be potential energy of the reactant. So go ahead and label that too.
Okay. So now that that's done, if we're looking at point E, you guys have probably guessed that this is the potential energy of the products. Again, you are producing your product, so it is at the end of the reaction. Now, we're not done with our labeling, but at least this is the stuff we know. Let's jump into stuff that's kind of new. So, I'm kind of bummed we're not actually teaching this to you in person, because there's a great demo with this ball that shows what point B is. So B represents something called activation energy. So we can also write it as E with a little a underneath it. So essentially what that means, it's the energy needed to get the reaction going. So if you think about it, if you're trying to push a giant rock up a hill, because that is very logical, it's definitely something you will do. If you just give it a little bit of energy, that rock is not going to go anywhere. You need to put in a specific amount of energy to get that rock to the top of the hill. That energy, so the energy from where you start to that very peak, that is called the activation energy. If at any point when you're pushing that rock up that hill, if you don't reach the top, if you don't put in enough energy, that rock will fall back down and will not go over the hill. So in a reaction, if you do not reach that activation energy, the reaction will not happen.
All right. So what you're saying is this activation energy is basically the amount of energy needed to push something, or not push, just the amount of energy for something to happen.
Exactly. So if we jump into point D, that very top of the peak, let's change colors here. This is called the activated complex.
So this is what we were trying to highlight before, and now you see it on the actual diagram. It is at the peak of the quote-unquote hill. Okay, so listen in on what this actually means.
So an activated complex is kind of a mix between what the products look like, what the reactants look like. So it's that kind of in between phase. So this activated complex is not the reactant, it's not the products, but a kind of halfway point between the two. So essentially, if your reactants are blue and your products are yellow, the middle point between those two things would be green. So not either one, but in the middle. So this is a very, very unstable spot. It doesn't want to be in that spot. It wants to be either a reactant or a product. And again, with that enough energy, you'll be able to push to become a product. Now,
So, key terms, it is unstable. Okay, at the activated complex point, it is very unstable. That they don't want to be at that situation.
okay, so the only point now that we haven't talked about yet is point C. So in a previous lesson, you guys talked about table I and that delta H value. And we said that delta H, kind of like how delta T worked for the MCAT equation, was the heat of the products. So again, your final conditions minus the heat of the reactants, your initial. So C represents, let me change colors, is delta H. So if you look at the end where I'm writing the orange here, this is your products and this is your reactants. The difference of energy between the reactants and the products, that is your delta H. So again, if delta H is completely new to you, go back to the enthalpy lesson because that's where we first introduced it. So as of right now, the picture is 100% annotated. So let's start jumping into the 10 questions below. We ready?
Yeah, we're ready. Question. We're gonna introduce the catalyst in a little bit, yeah?
Yes.
Okay. So, yes, I know you guys are like on the edge of your seats about this catalyst that we've been mentioning, because we will be adding that to your graph, okay, and what that actually means. So let's go ahead and proceed.
So jumping into question 1, it's asking if it's endothermic or exothermic. So before we had talked about delta H, and if it's positive, that meant it is endothermic because heat is absorbed.
Mm-hmm.
And then if you had a negative value, that meant exothermic because heat was being released. So again, it all comes down to this delta H value, the products minus the reactants. So a quick way to think of it is looking at where you started and looking at where you ended. So I know for our 6th period class, this came into a philosophy debate, not debate, but conversation, looking at where you start, looking at where you end. But we need to bring that kind of concept back here. So
Do we really though? That's so much fun. Yeah.
look at where you start, look at where you end, figure out where you need to go. Yes.
Like the journey that happened in between the start and the end, and to like analyze that. I think a very profound student had mentioned that one day. Do you remember that?
I do. So if profound student, if you think we're talking about you, we probably are. So essentially before we talked, that path was important, but here we essentially just care about where we start and where we end. So I'm highlighting in a green box now is where we started, where we ended. So look at it. Are we looking at where we started, looking at where we ended? Did we end higher or lower than where we started? So we ended higher. So if you end higher, that means you have to essentially absorb energy. And if you're absorbing energy, that essentially means you are endothermic, heat is absorbed. So if you're ending higher than where you started, that is endothermic. All endothermic potential energy diagrams will look the same shape-wise. The numbers may be a little bit different, but you will always end higher than where you start in an endothermic reaction.
Okay, so key terms. Endothermic, you're ending higher than you started. Yes, and energy the heat is being absorbed. Yep.
Yes.
Mm-hmm.
Okay. So looking at number 2, we essentially already answered it. It says delta H is calculated by determining the difference between the energy of the products and the energy of the reactants. In this case, delta H is. So again, like I had written just above this sentence, if you have a positive delta H value, it means you end higher, that is exothermic. If you have a negative value, that is exothermic, and heat is released. So in this case, our delta H is going to be positive.
Positive, yes. It's an endothermic reaction. So therefore, it is positive delta H.
Again, we'll calculate that value, so if you're a little bit confused now, don't worry. So let's jump down to number 3. So now that our picture is labeled, answering these questions will be super, super easy. So number 3 asks about point A. And point A is the very beginning of the graph, and that shows the potential energy, so PE, of your reactants, essentially what you're starting with. And so on that picture, the value of the PE of the reactants is 5 kilojoules. So that's how much energy is stored within the reactants.
Right. Okay. So the materials that you are starting with, that's how much kilojoules that those reactants have. Right?
Yes.
Okay.
So number 4 says point E is showing. Again, this is where you're ending. So this is the PE of your products. And if you were to follow the dotted line across to the y-axis, the value of that is
10 kilojoules.
10 kilojoules. Congratulations, you can read a graph.
Yay! Goals!
So essentially, these 10 questions is how the regents will ask you about this graph. So it's not hard. That's why we kind of saved it to the end of this overall topic. But it just takes practice. So looking at B is showing it's starting where the reactants are and then going to that top point. That is your activation energy.
Yeah, so earlier on we were talking about, okay, if you were like pushing a rock up a hill, the amount of energy it would take to push that rock up that hill is, in this diagram, like this is how it would look like. Okay, so we label this as B and we call it the activation energy. And then moving on and talking about the value of the activation energy, it's going to be 20 kilojoules.
So if we look at where that 20 comes from, we want to look at where we're starting. So our reactants have a PE of 5 kilojoules. And then the max value is 25. So essentially we want to figure out how much we change from where we started to that very peak. So you get 25 minus 5. And if you can't do that in your head, you do have access to a calculator. But that is 20 kilojoules.
Right.
So essentially what that means, you need 20 kilojoules of energy to get this reaction started so it's able to finish.
Right. Is this like on the regents? I feel like this one is.
This question, they love asking about activation energy.
Right, because a lot of times students will just look at the 25 kilojoules and think that that's the answer. But like you have to go ahead and make one more step and say, where does this start? Okay, and then you would have to minus that energy value from the 25 kilojoules.
Exactly.
Yes.
So again, you'll practice this more later on, but this is just kind of a very good intro. So number 6 is talking about point D rather. So point D starts at the very bottom and goes to the very top. So we can say that this is the PE of the activated complex. So again, that kind of intermediary, very unstable portion of the reaction. So here, all you want to do is follow the dotted line across from what that top peak of the energy is. And that gives you 25 kilojoules. So it's important for you guys to realize the difference between activation energy and the potential energy of the activated complex. So if you're confused, pause the video, take a quick look at it. There is a very important difference. Okay. Moving forward, number 7 is talking about point C. So like we had labeled before, that's showing you the difference between where you started, the reactants, and where you ended, the products. And so the difference between where you end and where you start, that is what we called delta H. And if we're looking at... What'd you say?
Reaction. Yeah. Like sometimes it's just good to know what it stands for too. All right. Yeah, go ahead.
Okay. So first we want to figure out where we end. What is our... So up here I had written the delta H equation. So the energy of our products is 10 kilojoules. And then the energy of our reactants is 5. So 10 minus 5, again, if you need a calculator, use it. You get 5 kilojoules as your delta H.
Right.
So looking at the number, is it positive or negative? If you're looking at it, you're like, well, duh, it's positive. That's great. And a positive delta H value going into number 8 means you are endothermic. And the definition of endothermic is heat is absorbed. So you'll see an example later on where delta H is negative, but right now it's just products minus reactants. And if it's positive, it's endothermic, meaning heat is absorbed. Are we okay for right now? If not, pause, go back.
Yeah, no, I think that's pretty good. At this point, it's a good time to review what we just said. Okay, it is a lot. So just review what the diagram, like the labeling of the diagram, the definitions, and what this actually means. Okay, I think we're okay to go ahead and move down.
Okay. So number 9 is something we've been kind of previewing all time, is the catalyst. So if you go back to the reading, the catalyst talks about how it speeds up the reaction by lowering the activation energy. So what it means on the graph. So I'm going to write this in pink. It does not change where you start. It does not change where you end. All it does, so the dotted line in pink, it lowers the peak. So now, again, if we picture that pushing a rock over a hill example, you could have a 100-foot hill and a 25-foot hill. The smaller hill takes a lot less energy, so it's a lot easier and it moves a lot quicker. So what the catalyst does, so let me label that.
So as Ms. Gallon is labeling that, what that really just means is like the amount of energy that it's going to take to push this rock up this hill would be much less compared to what it would normally have to push up. Okay? So she's drawing that right now. And then you guys can go ahead and label that dotted line as the catalyst. So it doesn't change where you start or where you end. That is super key.
Okay. So the Regents loves to ask you to either draw it in or pick it out of a lineup of pictures. But where you start doesn't change, where you end doesn't change. It only brings down that peak. So that's essentially what number 10 is. And number 9, kind of backtracking a little bit, all it changed was the activation energy. So it changes how much energy you need to kind of start that reaction. It does not change where you start. It does not change where you end.
Mm-hmm.
So that pretty much wraps up diagram number 1. So if we scroll down, thank you, iPad, for freezing.
So if you guys go ahead and scroll down, we're going to see the second graph that we have here. Okay, and in our directions, we're asking you guys to turn and talk with your neighbor, but you can't do that. Okay, and this is the potential energy diagram number 2. So you guys are a little bit familiar with this because it was part of our yo-yo, but there is a major difference. Okay, look at the products and look at the reactants. So notice that the reactants, we're starting now higher, and then the products, we are ending at a lower value.
Okay, so looking at this, Nathan said just, identify the very, very, very big differences from the first one. So take a second, pause the video, try to fill out these 10 questions, and when you're done, unpause and we'll show you the answers. So pause.
Have fun.
Welcome back. So if you've paused this, you've done the questions, and you're ready to go over this. So we're not going to spend as much time on this one because it's the same essentially as the first one.
Right. So we're just going to basically tell you the answers now, and you guys can go ahead and check if, you were correct.
So let's just label this very quickly. A represents the PE of your reactants. And then E is your PE of products. B, from the reactants to the very, very top, is your activation energy.
Right.
D is your PE of the activated complex. Woo! So exciting.
Yes.
Okay, and then the important difference here is C. C still is your delta H, but now the values are going to be different. If you notice, now you're ending lower than where you started with. That means overall energy had to be released.
So that means this was an exothermic reaction.
So that helps us answer question number 1. Exothermic because heat is released. And as you'll see later on, as we actually calculate the value, the delta H value is negative.
Negative.
Okay, so going through these questions, now that you've labeled it, it should be very, very easy. A represents PE of your reactants, and the value of that, if you follow to the y-axis, is 10 kilojoules. E is your PE of your products. Follow the dotted line. It is 5 kilojoules. Okay. Again, nothing that we've talked about so far has changed from the original example. 5, B represents the activation energy. And again, you want to figure out where you start and the very peak. So it's 25 minus 10 gives you 15. Okay. D is another thing that doesn't change, number 6. That is the PE of that unstable activated complex.
Right. And here, once again, if you're looking at it, the value is 25 kilojoules.
From the very, very bottom to the very, very top. Okay. Number 7 is where it changes here. And C is still showing delta H. So it's still showing heat of reaction. But let's take a closer look and find the value.
Wait, I have a question, actually.
Yes.
For number 6, the potential energy activated complex.
What about it?
No, never mind.
Okay.
No, it's cool. It's good. Okay, moving ahead, number 7.
Okay, so the delta H, it's still essentially final minus initial, so products minus reactants. So the energy of our products is 5 kilojoules. The energy of our reactant is 10 kilojoules. 5 minus 10 is negative 5. So that negative 5, that 5 is the energy, but that negative means energy is released, and that's exothermic. So
Right.
you're able to tell if a graph is exothermic by just looking at it, or you can further calculate the value. 9 and 10 are essentially the same as the first one. If you were to add a catalyst, it doesn't change where you start. All it does is lower that peak. So what I just drew was number 10. And then things that are affected by a catalyst is the activated energy. So with that being said, that is all the basics of potential energy diagrams that you need to know. Tomorrow, there is a sheet for you guys to just practice with this. And that's it. If you're confused, go back and read it, watch the video again, look at the YouTube videos we posted, look at the readings we posted, but this should not be incredibly difficult. Anything you want to add?
No, I mean, if it is difficult, just practice a little bit more. And it just is helpful if you do the Regents questions that will apply all of this stuff. Okay, and again, the things that we wanted to highlight were the activated complex and also the activation energy. Um, but yeah, just look over the stuff, review the YouTube videos posted for us, and you should be good to go.
Okay, so again, tomorrow we'll focus on practice, but have fun. You've learned a lot today, and goodbye. Have a lovely day.
Yay, bye.